The title of my talk is The Astonishing Simplicity of Everything. And I have to begin by saying that I told this title to a friend of mine a week ago who has teenage kids. And he said, "Oh yeah, the world seems pretty complicated to me." And so I'm going to be very careful by defining what I mean by simplicity. I hope to share with you some of the most amazing discoveries we have made recently about the universe, and the fact they're pointing us in new directions for our understanding of the universe, which is extremely exciting. So what do I mean by simplicity? Well, for a physicist, simplicity means, or simple concepts, are concepts which unify. They bring together disparate ideas and disparate knowledge, make sense of them, and simplify. I often like to say that a theoretical physicist is somebody who has a terrible memory, and therefore they want to make sure they're on top of everything while they remember nothing, and or as little as possible. So simple concepts are ones which allow us to explain the most we possibly can from the least possible number of assumptions. And so I'm going to tell you about the recent discoveries and why they show us, that they are pointing us to ways in which the universe has regular, predictable behavior, which we do not yet understand. And so this is pointing us at new, simple principles which we're trying to discover. So here's a rather beautiful picture of the whole universe that we can see. And we're in the middle, in the solar system, going around the sun. But there's this vast expanse of space full of galaxies. And of course, as we look outwards in space, we're seeing backwards in time, just because light takes time to reach us. So as we get to the outer reaches of the region we see this cosmic web, the structure of the universe as it began to form at early times. And we go further back, there's a dark stripe, which is the Dark Ages, we call it. And just before the Dark Ages is a bright red ring. That red ring is the hot plasma of the very early universe. The earliest thing we can see. And if we could probe through it, as we will be able to do one day with gravitational waves, we will be able to see right back to the singularity itself, the moment when space and matter emerged, and when everything was formed. Now, our place in this universe is in the middle, obviously. That's not because we're in a special place. Every other place in the universe, as far as we know, would have a similar picture around it, would be surrounded by a similar picture. But we're also in the middle in terms of scale. You see that there's a definite size of this volume of space. There's a number of galaxies, about 100 billion galaxies we can see, each one containing 100 billion stars. But what we've discovered recently is that space, empty space, is full of dark energy. It's a form of energy which is accelerating the expansion of the universe. The universe is growing in size, and the expansion is carrying other things away from us. And due to the dark energy, it's expanding faster and faster. And so it's taking the stuff, even the most distant galaxies we can see, taking them away from us more and more rapidly. As it does so, we'll see them turn red, go dimmer and dimmer, and disappear. And we will never see anything beyond those galaxies because of the dark energy. So there is a scale, there's a fundamental scale in physics. It's the scale defined by the dark energy, which limits the region of the universe we will ever see. And so that's the largest scale we know of. It's about 10 to the power 25 meters. The tiniest scale we know of in the universe is what we call the Planck scale. And that you can see right at the edge of the picture. You see, if we look out as far as we can, go backwards in time, following the universe back to the singularity. Imagine we are following a light wave that's traveling through this plasma. The whole universe is shrinking, the light wave is shrinking, it'll become more and more energetic. The Planck time is the moment those light waves are so energetic that two light waves encountering each other would form a black hole. And so they would disappear. We can't describe them after that, they'd be inside a black hole. That's called the Planck scale, a scale so tiny that if you try to squeeze a light wave into it, it has enough energy to collapse the space around it and make a black hole. So that's called the Planck length, and that's about 10 to the minus 35 meters. So we can go from 10 to the plus 25 to 10 to the minus 35. Now where are we? Well, the size of a living cell is about 10 to the minus 5, which is halfway between the two. In mathematical terms, we say it's a geometric mean. We live in the middle between the largest scale in physics, which defines the region we will ultimately see, and the tiniest scale, which is so tiny we can't even talk about space and time on smaller scales than that. So we're in the messy middle. And the astonishing thing about recent discoveries in physics is they tell us the universe is surprisingly simple and regular on the tiniest scale and on the hugest scale. It's only complicated in the middle. And so that's the sort of summary of my talk. I can take questions now. As I mentioned, we can look at it in space, we can look at it in time. If you look at any region of the universe, it would have a history like this, as far as we know. So you trace it backwards in time, it shrinks down to zero size. The space literally shrinks away to nothing. As you follow it forward in time, it's dominated by this dark energy, which is causing it to expand more and more rapidly. We don't know where it all came from. We don't know where it's all going. These are very profound clues, which we finally have the means to get to grips with. So here's a real picture. This is a picture made by the Planck satellite, the European Space Agency Planck satellite. It shows a projection of the whole sky which surrounds us, the spherical sky. So it's like a map from an atlas. And the pattern it shows is the pattern of the variations in the density across the sky. Those variations in density create a variation in temperature, and where the sky is hotter, you see a brighter radiation coming from it. Where it's colder, you see a less bright radiation. And that's what this picture is showing. Now, you can see immediately this picture has amazing symmetry. The universe is not a random mess on large scales. Why? Because these variations in the temperature are only 1 part in 100,000 from place to place. So to first approximation, the universe is absolutely uniform in all directions. Very strange, because given that we're only receiving the light from from these places on opposite sides of us, how did they know to be at the same temperature? They can't have communicated with each other through light because we're only receiving light from them now. But nevertheless, they are very close to the same temperature, these points which surround us in all directions on the sky. The second thing, which is not obvious in this picture, is what I call synchronicity. See, if you take a bell which vibrates at various tones and you strike it, all those vibrations are synchronized because they all got excited at the same time. And so if you look at the pattern in the sound of a bell, you would be able to detect that it was struck at one moment. And that's what happens with these variations of temperature. They were excited at the Big Bang. And subsequent to that, they have oscillated a certain number of times, and so you can't see it in the map. So what you do is a mathematical trick called Fourier analysis, which I'll talk about a little later. So you essentially look at this picture, but in a slightly different way. And what you see is this, that when you analyze the amplitude or strength of variations in temperature on different scales on the sky. See, in a different scale, it's like the length of a string of a musical instrument. It will vibrate with a different pitch. And so I call this pitch, the amplitude against pitch of the sky. And what you find are these wonderful peaks. These are waves which have oscillated once. They've hit their maximum just when we see them. These ones have hit their first zero. These have hit their second maximum. So we literally see the universe is a giant bell, was struck at the Big Bang, and everything is synchronized. So there's remarkable symmetry in this pattern. The universe is not a complicated thing at all. In fact, the whole universe is as simple as the simplest atom. If you think about a hydrogen atom, you know, how many numbers do you need to describe an atom? An atom's a pretty simple thing. You've got a nucleus, you've got an electron going around it, you've got the force of electrical attraction between the nucleus and the atom. And you've got a few details of quantum theory too, which I'll come to. But an atom is a pretty simple thing. Well, it turns out the universe, to describe the structure, you need one number, which is this number, 1 part in 100,000. That number describes the structure of the universe. Fewer numbers than you need to describe a single atom. So the universe turns out to be the simplest thing we know. The whole thing is the simplest thing we know. Isn't that amazing? And this is how to go from that pattern, which looks random, looks like a messy pattern. You know, it looks pretty random and unimpressive. But if I show you this pattern, so the way I've built up this pattern is by adding together waves of different wavelengths. And I've added them all up so they, whoops, let me do it again. When I add together the waves of different wavelengths, the result, it's giving me trouble, but the result looks pretty random. When you go to this Fourier picture of seeing how strong was each wave, they're all the same. And so the universe we see doesn't distinguish between scales, doesn't distinguish between how big something is. A wave that stretches right across the universe has the same strength as one 100 times or 1,000,000 times smaller. They're all the same. It's an unbelievably simple pattern that came out of the Big Bang. And here it is, more graphically. Here, imagine a sphere carved through space on which we can see what the hot plasma of the universe is doing as it expands. And you can see it's oscillating with these waves. And as the universe expands, the scale gets bigger and bigger and bigger. And ultimately, this will be the sphere that surrounds us today. And when we look out, we're in the inside of the sphere, looking out, and we will see this pattern, which is scale-free. Now, I want to show you, this is a little bit of recent research with my collaborator at the University of Toronto. This is us trying to calculate what happened in the first billionth of a second after the Big Bang. So the beginning of the movie, it loops around, but the beginning of the movie are these smooth waves filling space. This is the end. Let's wait for the beginning again. There, you see these smooth waves filling space. They look very benign. But as they evolve, you see they form shocks, sharp edges. And these shocks then collide, and they will generate all kinds of interesting effects. So this wasn't understood until very recently, and it's an example of how we are following our knowledge back further and further into the deep past of the Big Bang. This is probing energies beyond the Large Hadron, what the Large Hadron Collider can do, but of course only theoretically. Okay, so that's the big picture. The universe has turned out to be stunningly simple. Most theorists I know are dismayed by this, because it means that most of the models have turned out wrong. Because the models were all predicting, oh, you should get this or this specific feature or that specific feature. And what's happened is the universe has surprised everyone, that it's simpler than any of our models can explain. The same thing happened at the Large Hadron Collider, and I'm not going to dwell on it, but they were looking for the Higgs boson, they found the Higgs boson. Most of the theorists in the world were predicting lots of other particles would come along with the Higgs boson. But the Higgs is pretty lonely. And again, nature has used the simplest possible way. It's so simple we don't understand how nature got away with it. So the coming year is very exciting at the Large Hadron Collider. If they don't see supersymmetry, which was one of the favorite theoretical paradigms, if they don't see it, it will be a disaster for many people who've spent decades working on that idea. But personally, I would welcome it. I mean, as a theorist, you should be happy when you're wrong, because at least it meant your idea was testable, was worth talking about. Okay? It was worth talking about. I mean, if you can't be proven wrong, it's not worth talking about. So, but I'm not sure other people share that view. So let's go back to the beginning of physics and mathematics. Because the simplicity I've just told you about, we don't yet understand. Okay? Are we ever going to understand it? I want to persuade you the answer is certainly yes. In order to make the case, I have to show you how far we've come already. And it's ridiculous how far we've come, of course, when you think how briefly we've been thinking about these problems. So let's go back to the beginning of mathematics in Africa. 22,000 years ago, somebody in the Congo carved these markings on a bone, the Ishango bone. There are 60 notches on either side of the bone in very particular arithmetical patterns. And people who've analyzed the bone have concluded that this is not a coincidence. They weren't just playing with notches, they were studying patterns in numbers. So that's the beginning of mathematics, and you think of the significance of that. I mean, where would we be without mathematics? The idea of number is a strange thing. I mean, 1 or 2 or 3 don't exist as entities in the world. These are abstractions, idealizations, yet they work. You couldn't do finance without numbers. Actually, some people do finance without numbers, and it doesn't work. But you shouldn't do finance without numbers. So numbers are incredibly powerful. And again, this is a feature of simple ideas. They are unifying, they are unbelievably powerful, and they open the door to the future. And that's what happened in Africa. This you will probably all remember from high school, Pythagoras' theorem. This was the transition of mathematics into a theorem-proving subject, where you tried to prove things. You know, so what is mathematics, after all? Mathematics is just logic. It's the crystallization of logic. The ideas which are considered proven in mathematics are the most proven things we know, more or less by definition. Okay? That's what you mean by mathematical proof. So physics is a little different. Okay? Physics is logic applied to the real world. So Fortunately, the real world does seem to obey logical rules, mathematical rules. And it's a physicist's task to discover what those rules are in nature. Mathematicians don't mind if the rules are relevant or not to nature, as long as they are logically consistent. So Pythagoras, actually, didn't discover this. This result was known, but Pythagoras thought about how to prove it. That was the novelty. So we have a triangle with three sides, A, B, and C. And as you know, Pythagoras' theorem is that the area of the squares on the two shorter sides will sum to be the same as the area on the long side. And that was the first theorem in mathematics. Now here's a rather beautiful proof of this theorem, which will use some ideas which I'll need later. By the way, let me just comment on the notion of proof. A friend of mine in Africa once told me that the significance of proof, mathematical proof, it's an African mathematician, mathematical proof is connected to justice. Because in ancient Greece, one of their innovations was that you couldn't just accuse someone of something without showing, without arguing, without conclusively producing evidence that they'd done something wrong. So the idea of proof came along at the same time as mathematical proof. So logic and justice are actually very closely interconnected. So let's go back to our triangle, and you'll notice one of the angles is a right angle. That's the theorem only applies to right angle triangles. The other two angles I've labeled, and now we've drawn a perpendicular from this corner to the hypotenuse, the long line. And what's special about these two angles is that they are shared between two triangles. You see, this angle is obviously one of the three angles of the big triangle, but it's also one of the angles of this little triangle. This angle is shared between the medium triangle and the big triangle. Now, you know, if two angles are the same in two triangles, the third angle is fixed. Okay, so it means that all three angles in all three triangles have to be the same. Therefore, the triangles must be the same shape. If they're the same shape, it just means they're scaled up versions of each other. Okay? Now, what is the area of a triangle? The area of a triangle, well, you know it's half base times height, but even more primitively, you'd say it's a square. An area is a square of a length. Take a triangle of some shape, and I scale it up, the area is going to scale up like the square. Okay? So the area of this triangle is b squared times some number. The area of this one is c squared times the same number, and a squared times the same number. Why is it b, c, and a? This is the hypotenuse of the big triangle, that's the hypotenuse of the little triangle, and so on. So you see immediately that because the areas of the two smaller triangles are the same as the bigger triangle, you must have this formula. The square of A plus the square of B is the square of C. Okay, so that's a rather nice argument that for any right-angled triangle, this equation must be true. Now I want to introduce a more bizarre mathematical character, and it took people 2,000 years to make the next great leap in mathematics. Okay, geometry was pretty important. With Pythagoras' theorem, you could build pyramids and structures, and architects wouldn't make a living without Pythagoras' theorem. But it took 2,000 years before the next huge leap forward in mathematics, and that came about with this strange character I. So the problem was that the problem arose in solving equations. Mathematicians like to solve equations, that's what they do. So you write down x squared plus 3x plus 2 equals 0, or x to the 5th plus x to the 4th. So they were busy in the 16th century solving these equations. In fact, they had competitions to solve equations. And so nobles would set equations, and then people would arrive, and they would work desperately for a couple of days, and the one who solved the equation would win the prize. So there was a guy who, at the time, who discovered that if he imagined a number whose square was -1, then he could actually solve lots of equations. And he kept the trick secret. It wasn't published for 20 or 30 years, and then finally word got out, and this number I, the imaginary number, came into being. So it's a very strange thing. It sounds very counterintuitive. How can I have a number whose square is negative? We all learned in high school that a number times itself. Two negative numbers, a negative number times itself will give a positive number. So it's obviously not a negative number. It's not a real number at all. It's an imaginary number. Actually, in my inaugural lecture in Cambridge, I introduced this number and I didn't really explain it. And my brother is an economist who happened to be at the lecture, and I talked about imaginary things. And he said to me at the end of the lecture, if you allow yourself imaginary things, I'm not surprised you can do anything. But this imaginary number is very, very, very precise. There's no ambiguity about it. It's not a fiction as far as mathematicians are concerned. It's the real deal, this I. Now why? Because as soon as you've introduced it, you can solve all equations. Okay, so it's rather easy to show. I won't show it in detail, but it's rather easy to show using the concepts I will describe that any possible equation has a solution. Furthermore, any equation which, say I wrote down x to the 23 plus some number times x to the 22 and so on equals 0, there will be 23 solutions of that equation. And that's rather easy to see. If somebody wants to ask a question afterwards, be happy to answer it. That's called a fundamental theorem of algebra. So all of a sudden, with this one extra character in the game, a problem that had seemed impossibly complicated and difficult, because some equations seemed to have solutions, some didn't have solutions. Now all equations were on the same footing, and they all had solutions. It's an incredibly powerful, simple idea. Once people had, now it relates to Pythagoras' theorem as follows. Once you have the idea that you have this guy I, and this is a very valuable idea. It's not an iPhone or an iPad. It really annoys me when that was branded as I, because this is the I. Okay, I'm sorry. This I will be here for eternity. I'm not sure about the other one. Okay, so we take the I. Now, we are going to enlarge our space of numbers. We have a number x, which could be any number, from -infinity to infinity, an ordinary number. And then we have another kind of number, which is a multiple of I. So, and we put the two things together. We say, I'm going to allow numbers which have a real part, the x part, and the imaginary part, which is the multiple of I. Okay, so the dimension, suddenly I've gone to numbers not being on a line. They're now in two dimensions. I can go along the line, I can also go in the I direction. And so I can go along x and up in y, and I get this number, x plus iy. Now, one of the most basic and important functions in mathematics is the exponential function. We all know about exponentials because of inflation in prices. That's a bad thing. If prices rise by 10% per year, the prices are going to go through the roof. And they will follow exactly this law. If the x is 0.1 to represent the 10% growth per year, it will grow as e to the 0.1, where e is the number invented by Euler. Euler, most brilliant mathematician in the world in the 18th century. So we know about exponential growth. It applies to a huge number of things. So if you have bacteria multiplying, each bacterium doubles every 20 minutes. then the population of bacteria will grow exponentially. Compound interest, many, many things follow this law. In terms of mathematics, this is the simplest solution to one of the simplest equations, which is that the derivative of a function, meaning the slope, is equal to the function. So it's telling you that how much the function will change as you increase go along in x. The change in the function is proportional to the function. Solution of that equation is this exponential function. Okay, so it's a very basic function in mathematics. Now, it's not very good for modeling the real world. Sometimes it's good, because sometimes really things do go crazy, okay? But a lot of what happens in the world is rather regular. I mean, things don't just keep growing forever. So Euler, who invented this kind of mathematics, differential equations and these functions, decided, what happens if I exponentiate? You see, this is exponentiating a real number. So he said, what happens if I exponentiate this imaginary number? Okay, very natural question. Does it also go through the roof? Well, no. When you exponentiate the imaginary number, it goes round in a circle. Okay? So the exponential of an imaginary number times theta, where theta is a real number, it's an angle, actually. It's an angle here. It gives you the trigonometric functions, cosines and sines. And if you remember your geometry, the cosine is this side divided by that, and the sine is this side divided by that. And I've taken out the scale. I've just set the hypotenuse to be 1. So you see the fact that the exponential of an imaginary number gives you a point on a circle. And so as theta runs, this angle theta can grow, the point is just going to go running around a circle. Now that's like a lot of natural phenomena. So if something in nature goes back and forth, it's going to be described by mathematics like this. Whereas if it goes one way and explodes, it will be real numbers. Okay? So that's what Euler discovered. This formula here connects differential equations, which give you exponentials, to algebra, which gives you I, to geometry, which gives you these. Okay? It's been called the most amazing formula in mathematics. So I hope you're beginning to be a little bit impressed with I. Okay? Does a lot of good stuff for you at very little expense. So let's see it in action. So here we are. We have this circle, and the angle is the angle subtended by this pointer. And as the theta changes, this e to the I theta is running around. And you can see its real part is going backwards and forwards and backwards and forwards. And so if I use that real part to model a wave, which is also traveling upwards, as its amplitude is going back and forth, I get what we call a sinusoidal wave. So the wave is now following this function, which came out of trigonometry, through this construction. And it turns out this is how nature works. Basically, everything that goes back and forth in nature can be described in terms of functions which look like this. In particular, when Maxwell discovered the equations of electricity and magnetism, the astonishing discovery he made as a consequence of figuring out the right equations was that he could describe light. And here it is. Here's a light wave. The yellow arrows are the electric field. The blue arrows are the magnetic field. The pattern, this field pattern, moves along in space at the speed of light. And Maxwell showed the known laws of electricity and magnetism gave rise to light, and they predicted its speed, and it was correct within a few percent. So that I call the greatest discovery in physics of all time. to get out of some completely different phenomena, electrical forces and magnetic forces, and figure out all the right equations, and lo and behold, you predict light. See, it's not just one thing you predict an infinite number of things. Because it happens that the equations Maxwell found don't tell you the scale of the light, because those equations have no scale. So you can take a light wave and shrink it down to a very short wavelength thing, like an X-ray or a gamma ray, or you can stretch it up to huge radio wave, which is kilometers long. The undulations are kilometers long. And they're identical. As far as the equations go, they're all the same thing. Maxwell's equations have no scale, and that means they can be applied across all scales. So out of one equation, you've predicted an infinite number of phenomena. And of course, people didn't even realize there were radio waves before Maxwell's equations. These were realized as a consequence of the equations. They knew about light, okay, and when they knew there was an explanation for light, the natural thing to say was maybe there's some other waves. And that's how radio waves were discovered, and that's why people started to try to make radio waves and communicate with radio waves, and so on. So this is again one of those simple ideas that turn out to have incredible impact and universality. In fact, it would be fair to say that in physics everything is a wave, because when particles like the electron were understood better by Paul Dirac, who found out the equation describing the electron. What did he do? He tried to write down a wave equation. That was the route to discovering. The electron obeys a wave equation, even though it's a particle. As I'll explain in a moment, every entity we know of in nature has this dual facet. It's both a wave, it travels along like the waves I showed you, and it's also a particle. And so every particle we know has this property. In fact, you have this property. You probably don't feel like a wave, but I can assure you, you are a wave. According to quantum mechanics, you're a wave, and it spreads. Okay. Fortunately, it doesn't spread much in our lifetimes, but you are all spreading waves, I can assure you. Now, having discovered that physics works through waves and through this back and forth motion described so nicely by the imaginary number, which, by the way, any electrical engineer will tell you they know I very well. It's a very useful trick. But having discovered all that, there was one huge problem. See, waves don't really make sense in the physical world. If Maxwell was right, was absolutely right that light was a wave and that was the end of the story, none of the world we know would work. And the reason has to do with heat. Okay, so let's look at the sun. This is a beautiful movie of the sun. It should be a movie. I think it's frozen. Let me try and start it up again. There we go. So look at the sun. It's obviously very hot. It's shining at a certain it's shining at light at a certain wavelength, the wavelength of visible light, which is a fraction of a millionth of a meter, fraction of a micrometer. If waves really existed, as in Maxwell's theory, with no other caveats, the sun could not exist. For the following reason. You see, waves can carry energy. And the problem is that if you allow waves of arbitrary wavelength, you can fit an arbitrary number of those waves into any volume of space. Okay, so say we're sitting in this room, and I want to tell you about all the possible waves of the tiniest little wavelength you could imagine. How many waves could you fit in the room? Well, as many as you like, because I can make them as small as you like. Okay, because They're there. They're waves. They're solutions to Maxwell's equation. The trouble is, if there really was this infinity of possible short waves, they would carry the heat of the sun away in an instant. Because the efficiency with which it's when the sun reaches what we call equilibrium, thermal equilibrium. What is thermal equilibrium? It's when things jangle around randomly and explore all of the possibilities. And there's a fundamental property is that they tend to share out the energy among all possibilities. It's called equipartition. They share out energy. The trouble is you've got this infinite number of short wavelength things that you could share the energy with. Well, that's what's going to happen. And the sun would go out in a puff of smoke. Okay, so if Maxwell was true, the sun couldn't exist. And it's true of any hot object. The only thing that saves the day is that light isn't a wave. Okay? It's a particle. And that's what Max Planck discovered in 1900. Planck was hired by the German Bureau of Standards to help design light bulbs that would be more efficient. They needed to emit the maximum possible amount of light in visible wavelengths. And so that was his task. And so he had to make a theory of why is it that a hot wire glows at a certain temperature or a certain wavelength? Hot wire of a certain temperature, why is there a corresponding wavelength? And the more he tried, the more confused he got. Nothing made any sense because he kept losing all the energy into infinitely short waves. There are just so many of them. And so he hit upon a simple idea that light refuses to carry energy except in packets which depend on the wavelength of the light. So the short wavelength light, the very little waves, are incredibly fussy. The energy they carry is huge. And basically it says, if you don't have enough energy for me to take, I'm not taking any. and that's the consequence of why the sun is stable. So if you want to know, so Planck's law was that the energy light carries is a new constant of nature called Planck's constant times the frequency of the light. Frequency is higher the shorter the wavelength. And so now if you look at the sun, we know the temperature of the sun, we know the energy which is carried by each light wave. It's given by the temperature. And we also know the frequency of visible light. Just take the ratio and you get Planck's constant. Okay, so the sun directly if we know the temperature and we know the wavelength of light, we can just read off Planck's constant from the sun. Okay, so nature gives us these clues. It tells us the answer. We just have to be smart enough to listen. Well, Einstein came along. So when Planck proposed this idea, everyone thought he was nuts. It sounded very wild. Why can't waves take whatever energy they want at any wavelength? But then Einstein came along and he interpreted an experiment as confirming Planck's idea. So the experiment is called a photoelectric effect. You shine light at some frequency onto the surface of a metal. Sodium was typically used. And the light hits the surface of the metal and it kicks out these electrons, just kicks out these particles. And what happened in the experiment was a very strange thing, is that if you shone a certain wavelength and frequency of light onto the metal, you got out electrons of only one energy. Okay, and the energy was given by the same constant, Planck's constant, times the frequency of the light. So that graphically illustrated that the light was only able to give energy to the electrons in these quanta. And as I said, if light wasn't quantized, hot bodies wouldn't stay hot for very long. They would lose all of their energy into little light waves. Now, so light is a wave. but it's also a particle. And this is one of the incredible conundra in physics that to this day we still don't really understand intuitively. We know how to describe it, we know how to do calculations, but it's pretty damn weird. Okay? So here we have some light waves coming out of a laser, for example, pulses of light. They encounter two slits, and you might imagine when they went through those two slits, you have two bright patches on the screen behind. But that's not what happens, because the waves interfere. And so this is just like if you make waves in a pond. The waves you set up from this slit, from one object and another object, are going to interfere with each other. And so you get this interference pattern between the waves. That's a normal wave phenomenon. What is not so normal is when the light arrives at the screen, it doesn't arrive as a wave. It arrives in discrete hits, these dots of light. And that's where the light collapses and transfers its energy to the screen in a single quantum of light. So light is neither a wave nor a particle. It's a little bit of both. I like to think of the wave part of it as the exploratory part. Okay, so it spends all of its time exploring all its options, but it's pretty choosy about when and where it delivers. And when it does, it can only deliver in a fixed amount. And so it's a possibility wave. That's what the waves are. And in fact, everything is a possibility wave. Electrons have possibility waves, atoms, and even you have a possibility wave. You might be here, you might be there, but wherever you are, you're in one of those places. Okay? It's strange. That is how physics has come to be. Now, I say you might be here, you might be there. I'm talking about probability. And so physics made this jump from determinism, or the classical picture of the world as a machine, to another picture, which is that physics is about probabilities. But these probabilities, when you say probability, you tend to think of randomness and chaos and unpredictability. It's not like that. It's actually beautifully precise. The probability is you can predict the probabilities with extraordinary precision. Okay, so it's not total chaos by any means. So how do we predict the probabilities? Well, the imaginary number I comes to the rescue. You see, the most important thing about probabilities is they better add up to 1. If somebody gives you a model and they say, I think the probability for you to do this is 10%, that to do is 30%, and it's going to, something else is 25%. The first thing you should do is add up the numbers and make sure it adds up to 1. If it doesn't add up to 1, they don't know what they're talking about. Okay, probabilities have to add up to 1. Now then you say, well, okay, I give you some model, but I'm going to change those probabilities because the world evolves, the world changes, right? That's what physics is all about, the change in the world around us. How are you going to change those probabilities but always make sure that the total probability is 1? Okay? And the answer is you use Pythagoras' theorem again. So one thing I didn't tell you about Pythagoras' theorem is it actually works in any number of dimensions. You might think it only works in 2 dimensions for triangles, but actually if you made a box, a 3-dimensional box, and you measured the long diagonal, the Pythagoras theorem would still work, that the sums of the square of the 3 edges of the box would equal the square on the diagonal. And it actually works in any number of dimensions. The world has a lot of dimensions to it, but Pythagoras' theorem works for all of them. So you want to make a probability that adds up to 1. What do? You pick a circle, or in this many-dimensional case, a sphere, with a unit radius, single radius. And you say, I'm going to associate to some property, a real number and an imaginary number, x plus iy, and because this lies on a sphere, the sums of the squares are guaranteed to be 1. Okay? So what is change in the world? Well, change in the world is just this point moving around on the sphere, which is actually in many, many dimensions. So the constraint is, if you're going to describe probabilities, you better make sure that point stays on the sphere so that your probabilities all add up to 1 by Pythagoras' theorem. And that, in a nutshell, is quantum mechanics. That is the theory of quantum mechanics. Quantum mechanics is the question of how do I ascribe reality with probabilities? How do I change these probabilities while making sure they always add up to 1? That's called unitarity, which is a nice word used for physicists. And if you're a physicist and you violate unitarity, you're in big, big trouble. Okay. So now we know we have waves, but we know they're a bit weird. They come in these quanta. They can only carry energy in packets determined by their wavelength. And how do we model the atom? Okay, so Niels Bohr was trying to think about the atom. The atom didn't make any sense from a classical point of view because the electron, which is orbiting the nucleus, would emit radiation and spiral inwards and into the center of the nucleus in no time at all, if classical physics was valid. You had to stop that happening, just like we had to stop the sun losing all its energy into tiny wavelengths of light. So the one thing you know about waves is they have standing waves. You can have standing waves. So you have some waves in a box, and the wave just oscillates like this, like a rope held at two ends. And so it can either have one, actually half a wavelength in the box, or one wavelength, or 1.5. So the number of these zeros of the waves, here we have 1, 2, 3, 4, 5, 6. So that's the 6th mode in the box. We can have the first mode, the second mode, the third mode, and so on. So waves naturally come in these discrete modes. If they're quantized, they can only carry energy in fixed packets. So this is what Niels Bohr did. He imagined the hydrogen atom. Here's the nucleus. And these are the electron, the possible waves the electron can follow. The electron goes round the nucleus, but when it goes round, it can go round in a certain number of wavelengths. In the circle inside, it goes round in 1 wavelength. In this one, it's going round in 2 wavelengths, 3 wavelengths, 4 wavelengths. And these, he conjectured, were the energy levels of the hydrogen atom. He didn't quite formulate it this way because people didn't know that electrons were waves at the time, so he did it in a more ad hoc way. He quantized the angular momentum of the electron, but it amounts to the same thing. So this was the model of the atom, spectacularly successful, but not really understood until people understood how an electron can be both a particle and a wave at the same time. So the wave properties are crucial to understanding the structure of atoms. Now let's go back to light, because as well as giving rise to quantum theory, and the way it gave rise to quantum theory was by creating this paradox that you could have waves of arbitrarily short size. As well as doing that, light gave rise to the theory of relativity. And the reason was very simple. If I know the speed of light, that immediately doesn't make any sense in Newtonian theory of mechanics. Because in the Newtonian theory, which is the common sense theory, if something is traveling at a certain speed and I travel afterwards, its speed will go down. It will be traveling more slowly. So you chase after something, its speed relative to you has got to go down. Right? That's absolutely common sense. But it's absolutely wrong. Okay? Because light travels at the speed of light, no matter how fast you chase after it. Okay, it's a very bizarre fact, but it was immediately clear from Maxwell's equations. Maxwell's equations predicted the speed of light. That didn't make any sense. How can you predict a speed? Well, the only reason you can predict a speed is because that speed is the same for anybody. So, light has this speed. All these waves travel at the same speed. It doesn't matter how fast you're traveling, they will always travel at that speed. So that gave rise to the theory of relativity. So I'm going to show a little movie which illustrates this. Imagine I have a little, let me go back a little bit and start it again. So I'm going to have a little trolley with a laser in the middle, which is going to emit pulses of light in two directions. We're going to look at the trolley, first of all, standing with it, or traveling with it. It's traveling down some road, and we're going to be traveling alongside it, and watch those light rays going. That'll be a pretty obvious picture. Then we'll say, no, imagine I stand on the side of the road, and the trolley goes past. What do I see? The classical picture is that the light emitted forward is going to be going faster, and the light emitted backward is going to be going slower than the speed of light. Okay, so that's what we'll see in this first movie. This is made by an engineer at IBM, this movie, called Udi Aharoni. So here we are. We're plotting another dimension. This is time. This is time going upwards. Let me show you that one again. So the cart is moving along the road, but we're going to plot this with time going perpendicular just so that we can see the history of what happened. So time is going along here. Every time the laser emits these two pulses, they travel outwards. And you see they're going exactly at the speed of light because they go 1 unit along and 1 unit down. Okay? They're going at 45 degrees, that's the speed of light. Now, if I was standing on the road, watching the trolley go past, this pulse would be going much faster. Let's imagine the trolley is going at the speed of light, or nearly the speed of light. This pulse is going at twice the speed of light. This pulse is going hardly going at all, because it's going, the trolley sending it backwards, but the trolley itself is moving very fast forwards. So that's what the classical picture of the light trajectories would look like, and it's the reasonable one, the naive one, but of course it's wrong. So the problem is that when you do this transformation between standing with the trolley or watching the trolley move past you, the first one, let me go back to this one. Sorry, let's go forward again. You see, in this one, the light's not going at the speed of light. It's not going at 45 degrees. One of them, these lines, is nearly vertical, and the other one is more horizontal. So Einstein thought this is wrong. Why? Because the light's not going at the same speed. He suggested this one. So basically, you stretch time and space so that the light is always going at 45 degrees. It's always going at the speed of light in this picture. As you can see, the place where the light hits is, well, the light speed is always 45 degrees. The place where the light hits is at a different time. So any notion of simultaneity is gone, because they were simultaneous if I was traveling with the trolley, but now I'm moving relative to the trolley, they're not simultaneous anymore. So lengths change, times change, and simultaneity is gone. So here's the picture, the correct physical picture, that the light wave took a very short time for the back of the to hit the back of the trolley, takes a very long time to hit the front of the trolley. The spacing between these pulses is longer. This is time dilation. So if you want to stay young, you travel a lot. Okay? Because then the time between the beats of your heart will be much longer, okay, for somebody else watching you. So this is a sort of pictorial explanation for all the puzzles of relativity. Now, so again, this is a profoundly simple idea, but it's ridiculously hard to see it in the first place. I mean, who would have questioned the existence of space and time as separate entities? Nobody would have, unless there was this paradox posed by Maxwell's theory, and it took Einstein to see the resolution, which is that time and space depend on the observer, depends on who's looking. The measurements you make depend on how fast you are traveling. So it's extremely simple, but it's not easy. Okay. Once you see it, it explains an infinite array of phenomena, but to get to that point is very tough. However, once you've started to say that space and time are connected together and change from different points of view, it isn't too much of a step, but again, it's one of those simple leaps to say maybe space and time can bend. Why do they need to be that perfect square grid? Why can't we distort space and time like this? And that was the essential intuition that Einstein had, which led to his theory of gravity. So the Earth or the Sun bend space and time, creating a depression around which other objects can orbit, pulled in by the gravity. It's a beautifully simple idea, extremely difficult to reach for most humans. And of course, as soon as you do that, if you make space and time malleable, you bring into being the possibility that all of the space in the universe came out of something much, much smaller. Okay, the whole size of the universe came out of it, and that was the consequence of Einstein's theory, which even he didn't see. Okay, so it took Alexander Friedman, a young Russian, to stare at Einstein's equations and to realize that actually they can describe an expanding universe. So in an expanding universe, space itself expands. What I've drawn here is light coming out of the Big Bang, and those light waves, as the universe stretches, their wavelength is stretched along with space. They get longer and longer. And of course, if you're a cosmologist, you're more interested in this picture. We want to look outwards and backwards, and this is what we're tracing, is that we're tracing the light which came to us and trying to figure out what on earth happened then, when there wasn't any space or time at the singularity. So, I'll say something about that shortly. So these ideas of quantum mechanics and relativity led to this equation. This is the equation which summarizes all the physics we know. It is a simple equation, I can assure you. It is amazing that there are almost no phenomena in nature which we know of, which cannot be described by this equation. So it's a huge achievement of physics to be able to write an equation which summarizes the basic laws of physics in one line. Okay? Now you'll see in these formulas some characters you know already. E, it's 2.718, Euler's number. You'll see I, the imaginary number, it's right in the middle. You'll see Planck's constant, h. It's called h bar here because it's h over 2 pi. And then you'll see all this junk here. And all that junk does is tell you how that angle changes in psi. Okay, so psi lives on this sphere in a multi-dimensional space, and I've got to keep the probability 1, so things wander around the sphere, and the junk tells you how things wander on the sphere. Now, the junk is not such junk. There's Einstein's theory of gravity. It's the curvature of space and time that comes in. Maxwell's theory of electricity, of electromagnetism, and then the weak force and the strong force are summarized here. Dirac's equation for the electron. And I have to tell you one story about this equation. So Dirac was a pretty amusing character. There's a biography of him called The Strangest Man. And he was very strange. I met him when I was a graduate student, and he gave us a 1-hour-long lecture on why physics was not going to make any progress unless we understood the number 137. Okay? That happens to be the inverse of the fine structure constant. It is a number in physics. We have to understand that, otherwise we won't make any progress. So he was a very strong-minded person. Dirac went to Princeton, where he met Richard Feynman, very famous young American physicist. And they met each other. It was a little bit awkward, and Dirac was socially pretty inept. And he said, the only thing he could think of saying to Feynman is, do you have an equation? Knowing, of course, that he had an equation, Dirac had an equation, which describes 3/4 of the known particles in the universe. Okay, the Dirac equation. It's a pretty amazing equation. So obviously this was a mild put down. So Feynman was a graduate student, okay? Feynman says, yeah, actually I do have an equation. It's really a rewriting, but it's a rewriting of Schrödinger's equation in terms of this integral. Okay, and he explained it in words to Dirac. Dirac said, oh, that's interesting. That was his highest praise. That's interesting. So Feynman and Dirac discussed this equation. So it's surprisingly simple. It's not the final story. One way to think of it is there are particles which don't have any spin. The Higgs boson is one. It doesn't spin around. It's just a field that exists at every point in space and has particles and waves that it can describe. So there's the Higgs. It has spin 0. There are these kind of particles that spin half, like the electron and neutrinos. We have photons, which have spin 1, and gravity happens to have spin 2. So basically we have 0, half, 1, and 2. 3 halves is a little bit of a problem. Nobody has figured out how to properly describe 3 halves. But, you know, essentially this is all that's possible. That's what you should take away from this equation. It's not so much the details. Once you accepted relativity and quantum mechanics, you're pretty much forced into this formula. So, and spins beyond 2 seem to be not possible. With field theory, you need string theory, for which there is no evidence. So, okay, so there are a few other little details. Neutrino masses, I already pointed to. These are clues towards unification. These neutrino masses are pointing towards unification at the Planck mass. I mean, it's very tantalizing, but it's also very remote from any current experiment. And we have the dark matter. There's 25% of the energy in the universe is in stuff which clumps around galaxies, and we don't know what it is. So here is LHC. It's running again this year. It's tremendously exciting. It's probing scales of 1/1000th the size of an atom, 13 TeV, and they hope to see new particles. We're waiting with bated breath. The dark matter. We can see the dark matter. We don't know what it is. Experiments at Art McDonald's lab, Snow Lab, are searching for all different candidates, many different candidates of dark matter. We're seeing black holes. Within the next 2 years, we will have images of black holes. I think you saw those on the slide before this lecture from a young researcher here. And we're going to see gravitational waves within the next 5 years. Gravitational waves telling us what happens when black holes merge and collide, and also with neutron stars. And ultimately, we'll be able to use these gravitational waves to look back to the Big Bang itself. I wanted to show you this. It's a slide from Convergence, from Emmanuel Bloch, who does quantum experiments. This is just giving you a picture of what is now becoming possible. It's an array of atoms held in place by lasers, so it's called an optical lattice. And the individual atoms can be manipulated. and in particular their quantum properties can be manipulated. So the collective body of atoms can enable you to do incredibly precise things. So for example, the standard clock now used relies on a single atom, right? That's the most accurate clock in the world, or was, until these came along. These put thousands of atoms into a similar state, reduce the noise, and enable much more accurate clocks. So clocks using optical lattices, atoms in optical lattices, can now reach accuracies of better than 1/10 of a second over the age of the universe. So these clocks are accurate to 1 part in 10 to the 18 in precision. So using these devices, one can build incredibly sensitive detectors, and this is what's coming. Of course, we're all excited about quantum computers and manipulating qubits instead of bits. So instead of the closest analog to the zeros and ones in your computer, the simplest element of quantum reality is a single spin of a particle, and this is the motion it can perform. It's actually Pythagoras' theorem in action. The qubit is exploring its possible states and satisfying Pythagoras' theorem because the total probability has to be 1. So if you build a computer out of these things, it will be vastly more powerful than anything built out of digital technology. So I want to end just by talking about something I'm most interested in, which is this guy, the tiniest puzzle in science. How did everything come out of nothing? It's very puzzling indeed. But we've just put a paper out describing how a universe can bounce. It can contract with the light waves going down and bounce again. Mathematically, this is allowed. It looks pretty bad when all the light is on top of itself. But you'll remember that light doesn't have a scale. You see, so whereas we would look at the universe and say it's shrinking, in fact, the light doesn't see the shrinking. It's due to the scale independence of Maxwell's equations. And so that's a new symmetry of Maxwell's equations, which can be used to describe what happened at the Big Bang itself. The big puzzle is this one. See, the world's most expensive telescope has mapped the dark energy, and that's what it looks like. Okay. It's absolutely featureless. The wonderful thing about it doesn't matter how fast you're traveling, it looks exactly the same. Doesn't matter what you do, the dark energy is the one thing you can count on to never change. And so that's the dark energy. Now why is it the biggest? Well, it's the biggest puzzle because it fills the universe. It's 70% of the energy in the universe, and we don't know what it is. It's totally dominating the expansion of the universe. It will control our future, and we don't know what it is. Here's some of it. This is the vacuum in nuclear physics. So what holds particles together in atomic nuclei is something called QCD, quantum chromodynamics. It's basically a version of Maxwell's theory, but it's a little bit more complicated, and it has fields called gluons, which do this. And they're everywhere in the vacuum. And if these things weren't there in the vacuum, then nuclei would fall apart. So we know the stuff is there. We know it has energy. We can calculate the energy in these fields in the vacuum. And it's a large number. It's a very large number. We know there are many other sources of energy. The electron gives energy in the vacuum. The electromagnetism does. The Higgs field does. Somehow, all of these vacuum energies add up to this. Okay? They add up to 0.0000 with 120 zeros, 1. So the vacuum energy is tiny in any sensible units. It's ridiculously small. But because there's so much of it, it fills all of space, it overwhelms everything else in the universe. So, huge puzzle for physics. How did the universe tune itself into this very delicate balance? Some people propose a multiverse, and this is called by some the end of physics. That they say, look, basically what they're saying is some things we'll never explain. So let's just postulate that there are infinite number of possible universes, and we happen to be in one that came out like this. Okay? There's not much more to it than that. And it just happened that string theory was reaching a crisis of predictability. It couldn't predict anything. There are too many possibilities in string theory. So this idea came along at the right time, and people embraced it and said, okay, maybe that's the solution. The universe is wild and random and unpredictable on large scales. The problem with this theory is that it can't make any predictions. Nobody can define probabilities. There's no Pythagoras theorem in this theory. It really is just wild randomness. And so some of us believe there's probably a simpler answer. And I think, for me, the fact the universe is so simple around us indicates this multiverse idea is probably wrong. So instead, what I'm much more interested in is the idea of a cyclic universe, that the Big Bang came about when matter collapsed, the Higgs field was restored, scale symmetry became perfect, you entered the big crunch, a Big Bang emerged, and the universe undergoes endless cycles of destruction and creation. So that's a possibility. It's only a mathematical model. But the amazing thing is we're at a point where we will be able to test. And so we shall see. Thank you very much.
Excellent. Excellent.
Thank you.
You can go to the center stage. Yeah.
Sorry?
Yeah.
Okay.
Very good. All right. Thank you. Wonderful. Now we've gone a little long, but there still must be some good questions, and we want to hear Neil talk just a little bit longer. So I will go to the questions. I can go online first, and if there's questions in the theater, just make your way to the microphone, and we'll get your question asked. So, Neil, the first question we'll take from our Twitter feed, and the question is this: the picture you showed of the whole universe at the start of the talk is just the visible universe, right? What's outside the outer ring?
Yeah, great question. So the naive answer would be more of the same. Okay, that the universe, naively, why shouldn't we just extrapolate? We can't see it, but doesn't mean it isn't there, so why not just imagine it's there? The trouble is the problem gets more difficult because of the dark energy. The dark energy means that not only can we not see it now, we will never see it. The stuff that's beyond what we can see now will never be seen by anyone because the dark energy is expanding it away so quickly that the light from that stuff will never reach us. Okay? So in that situation, it seems to me it's much more fundamental, this issue. Is there really a universe beyond? Or is it a figment of our imagination? Now, the one thing we've learned in physics is that if you talk about concepts which are untestable through any conceivable experiment, you're probably not making sense. Okay. It's, at the very least, it's uneconomical, because you're having to talk about stuff which could never, in principle, ever be probed. But it is more likely a sign that your whole formalism is wrong. Okay, so that's the profound, that's a crisis, I would say, which the dark energy has put us into. In other words, the dark energy combined with Einstein's theory of gravity, the expansion of the universe, is telling us that that theory necessarily has to talk about a lot of things which we can never, in principle, ever test. And to me, that's probably a sign of a problem in the theory. Why would, I mean, it comes down to some very basic philosophical beliefs, is the universe comprehensible or not? And I think we've come so far, and you think of the amount we can understand, it's crazy. Why would we say now, we've reached the limit, we'll never understand anything else? To me, that's obvious nonsense. So I think it's a challenge to us. We have to make better theories which don't refer to things which can never possibly be seen. And what are those theories going to look like? We have some clues. We do have some very, very good clues. That maybe the tiniest scale, you see, I mentioned the tiny scale is simple. The big scale is simple. All the complexities in between. Maybe there's a relation between the tiny scale and the big scale. If there is, that would be a totally new type of physics. We've had hints of such possibilities in string theory, but they've not really been used in real physics. So why do we think that big things are different than small things? If they're both extremely simple, maybe they're the same. So I tend to think that is where this is leading us.
Thank you. Let's take a question in studio.
How do you reconcile a cyclic universe with dark energy? If dark energy is causing the universe to continually expand at an accelerating rate, how can it ever collapse?
Wonderful question. So until the Higgs boson was detected, I wouldn't have had an answer. Okay? When it was detected, I didn't have time to talk about this, but when the Higgs boson was discovered, its mass is at a very special value. It just happens. It's at a value where the Higgs field vacuum we live in today, so in empty space today, the Higgs field takes some value. It's stable there. Okay? But at the value measured by the Large Hadron Collider, there's another value for the Higgs field, which has lower energy. And so our vacuum, the one we live in, could tunnel. In quantum mechanics, this is allowed, could tunnel into the other vacuum. In other words, the dark energy could go unstable. Okay? And that might be, it's very tempting to believe that is what would initiate the next Big Bang.
How long?
Well, you've no need to panic. According to the measurements at LHC, the vacuum we're in is stable for 10 to the power 500 years. Okay, it's a long time. Do we take that seriously? I don't know. There's also the question of when you make a black hole. When matter collapses to make a black hole, inside the black hole, you get a singularity. And we don't yet know what happens there. It could be that's the birthplace of a new universe. We don't know enough. But
thank you very much.
Thank you.